Time for the final talk of this session. It's a pleasure to welcome Hynek Paul, who will tell us about non-analytic terms of string amplitudes from partial waves. Please take it away.
Thank you, Ollie. Thanks for inviting me to this nice parallel session. I'll be talking about joint work with Yutin Huang and Michele Santagata. The paper appeared this summer, and we just uploaded a version 2 where we fixed some typos, so please look at version 2. So my talk is designed to be rather pedestrian, so please bear with me. I will try to guide you step by step, and I will try to avoid many of the technicalities. The talk is divided into two parts. In the general part up here, I will try to convince you that an easy way to compute such iterative S-channel cuts is very easily done in the partial wave basis. And in the second part, I'm going to apply the methodology developed up here to the type 2 closed string amplitude, about which we already heard some details. And in particular, I'm going to predict the logarithmic structure of the low energy expansion at higher genus. So let's get right into the partial wave expansion. As an introduction, let's consider the loop expansion of some 4-point scattering process of massless particles. So it's important that this is the particles are massless and they are external scalars. So this is a scalar scattering amplitude, and we know, okay, there is some, if we have some dimensionless coupling, we can expand in the small coupling, and we are instructed to sum over the Feynman diagrams. So there will be a crossing of these diagrams plus many other diagrams, and indeed, if we want to compute the full amplitude, this is generally very hard. However, there is a part of the amplitude which is easily computable, as I will show in the following. If we focus on something on an object which we will call the leading log, so at L loop order, induced by the massless S-channel, by the massless tree-level exchange, we will see that there's always a log to the L, where L is the loop order of minus S in the amplitude. So the L loop amplitude will contain log to the L S piece plus crossing of this. So this is the leading log stratum. We call this the S-channel leading log. And of course, there will be all the lower logs in S. And I will convince you, hopefully, that this coefficient can be computed easily through the partial wave expansion. So let's recall from unitarity cut, essentially, that this part of the L loop amplitude you can just compute by gluing trees. So how does it work at one loop order? At one loop order, we know that the S-channel discontinuity of the amplitude can be computed by such a diagram where the cut instructs you to take two tree-level, that's what the 0 stands here for, two tree-level amplitudes, and you need to integrate over the two-particle phase space. And taking this discontinuity in S, defined as the amplitude slightly above minus slightly below the massless S-channel cut, exactly picks the coefficient of this log S. So instead of bothering with this two-particle phase space integral, we employ the partial wave expansion. We take our amplitude, expand into partial waves. So these guys are the Gegenbauer polynomials. They depend on the scattering angle, and by AL, I denote the partial wave coefficients. And crucially, key property is that this just trivializes the phase space integration. So the partial waves, they are orthogonal with respect to each other under this two-particle phase space integral. So let's go back up here and plug in the partial wave expansion. On the left-hand side, I will find the partial wave coefficients of the discontinuity of the one loop amplitude. Using this orthogonality property, I will just pick the product of the two tree-level partial wave coefficients. So we are instructed to simply square the tree-level partial wave coefficients. This generalizes very easily to L loops. So the L loop amplitude will have a log to the L of minus S, which we can pick by taking L iterative S-channel discontinuities corresponding to computing such a diagram. And in terms of the partial wave language, the L loop discontinuity is, again, computed by simply the L+1 product of the 3-level partial wave coefficients. And if we wish to recover the function in front of the log L, we just take the result. I guess this should be a L+1. Sorry about the typo. Sum against the partial waves, and this will give us back this function. And as a comment, and this is already hinted in this picture, this construction is very general and applies to any EFT. So there can be some massless exchanges, but also some contact interactions. Are there any questions about this first basic part? Any complaints? No. Very good. So let's go to the second part of the talk, where I will apply this, precisely this technology to the type 2B closed string amplitude. So as a motivation, well, I wrote this sentence before I knew this was recorded. So despite much effort, I think, I still stand by this statement. Not that much is known beyond genus 1, although we just heard talks how to compute higher genus string amplitudes. Luckily, I put some qualifications to this statement. So, for example, at genus 1, the low energy expansion is very well studied, and more recently by Olli and collaborators, for example, the direct worldsheet computation of these non-analytic terms at genus 1 has been systematized. There are some results about genus 2 and 3 amplitudes, so you can write down the formal expression, but really working with those and extracting the alpha prime expansion is still very difficult, although Carlos and collaborators have managed to, I believe, work out the first term in the alpha prime expansion at genus 2 and 3. And furthermore, there are some non-renormalization theorems known for the 3 first protected terms. And there is a very nice interplay with S-duality also. In any case, I still stand by the first statement. So any partial higher genus result, I think, will be a valuable reference for future worldsheet computations, which should be underway, hopefully. So let's get back to the amplitude. We will consider the massless closed string amplitude, which describes the scattering of gravitons plus all the superpartners. In string perturbation theory, it admits the following genus expansion. So what are all these ingredients? So the amplitude depends on the 4 external momenta and polarization vectors. Luckily, due to maximal supersymmetry, all the dependence on the polarization vectors is taken care of by this R⁴ polarization tensor, so we don't need to worry about this. What's left behind is a scalar amplitude, which depends on the Mandelstam's S and T. And compared to the previous example, now there is an extra parameter, alpha prime, which will lead to a richer story of leading logarithmic terms. So recall from part 1 that all we actually needed to compute these leading logs is the 3-level amplitude. In this case, we can call it the genus 0 amplitude, which is given famously by the Virasoro-Shapiro amplitude. And if we take a low energy expansion, we start with 1/STU. That's the supergravity term. Alpha prime cube corresponds to the R⁴ correction. Alpha prime to the 5, the 4R⁴ term, plus an infinite tower of higher derivative corrections, whose coefficients, well, are encoded in here. So let's employ the partial wave expansion, and we will do this order by order in alpha prime. So for the first term, decomposing 1/STU into partial waves gives us the partial wave coefficients, which are now denoted by epsilon, and the superscript here is not the loop order, but it's the order in alpha prime. So the first term is alpha prime to the 0. And in fact, this term has infinite spin support over all even spins. Let's look at the higher derivative corrections. They all have the feature that their partial wave. Yes, that's a Pochhammer thing. L plus 1 Pochhammer 6, yeah. These higher derivative corrections, they all have the feature that the partial wave expansion is spin truncated. That's because these guys here are just polynomials in the Mandelstams. Yeah. Okay, so let's take these partial waves and the 3-level partial wave coefficients, and how do we compute the leading logs from this. So we're instructed to take simply products of those. However, due to this extra parameter, there is some grading, so we need to be a bit careful how to organize the alpha prime expansion at higher genus. And this is summarized in this formula, essentially. So on the left-hand side, I have the partial wave coefficient of the genus H leading log at order alpha prime to the n. And this will be given by a product of 3-level partial waves with the constraint that I need to now sum over all the permutations of the ni's such that I get the correct order in alpha prime on the left-hand side. And bear in mind, there is an extra shift. So in kappa 10 squared, there is an extra factor of alpha prime to the 4 hiding. So the left-hand side is for every unitarity cut, I pay the price of an extra power of alpha prime to the 4. I will illustrate this in a nice table momentarily. And this comes essentially from this Sewing relation, which this polarization tensor satisfies once I sum over all the exchanged two-particle states. So as a summary, at genus H, I again need to take a product of H plus 1 3-level partial wave coefficients. So let's go to this, which will be a huge table. Up here, I label the alpha prime expansion going to the right, and starting here, there is genus 0, and the genus will increase by going down. At genus 0, we have higher supergravity plus the higher derivative terms, which we've seen before. So let me denote this by S. This notation here, so R is schematically for R to the 4, and the subscript 0 everywhere stands for that. This is the genus 0 contribution. These are the terms in forest green, and they correspond to all the known analytic terms. So let's go to genus 1 now and implement our procedure of multiplying partial wave coefficients. Taking the supergravity partial wave coefficients times itself. So you can imagine that this vertical bar is the S-channel cut. There is a single log which is produced by these terms. S/S is at order 0 times 0 plus 0 plus 4 coming from the Sewing relation. So I arrive at this order here. Similarly, I can take supergravity times R to the 4th term, giving me this term here. And as you see, there is some combinatorics which kicks in rather even at rather low orders of alpha prime, that there are many different gluings which produce terms at the same order. Yeah. And computing these, plugging these results for which we get from multiplying partial wave coefficients back into the expansion, summing against the Gegenbauers, we simply reproduce the known results from the literature. But now we can do much more. We can go to higher genus with exactly the same method, taking supergravity partial wave coefficients 3 times now, mixing different terms will produce an interesting pattern of leading logs at genus 2, which we can easily compute. So these are new predictions for leading logarithmic terms at higher genus. We can do genus 3 very easily, and in fact, we can just fill in the entire table with leading logs. And yeah, I forgot to mention that the color coding here is that this beautiful red stands for all the leading log terms. However, this is not the end of the story. There are further analytic terms at higher genus, and this is for the experts in the room. We know that the higher derivative corrections, there is some modular completions of these functions, and the first three terms, for example, they are given by Eisenstein and generalized Eisenstein functions. These are the protected terms, and they all have a finite number of higher genus corrections. So by the same reasoning, we can now take products of genus 0 terms and genus 1 terms and so on, and this will, by exactly the same reasoning, will give rise to subleading logs. So wherever there was a gap before, there is room for other terms, and we can fill this in, and here I note the subleading logs in deep sky blue. They are subleading logs with respect to the leading logs. So here, for example, at genus 2, the leading logs is a log squared coming from 2 cuts, and this term, for example, comes from 1 cut. So again, there are now, you can do all the combinatorics and fill in this table. And by the same reasoning, again, we can access sub-subleading logs, etc. And this gives rise to the full full structure of non-analytic terms at higher genus. So this reveals our method is very simple and reveals a very intricate pattern of logarithmic terms. I had one comment for the experts about if you're interested in transcendentality of certain higher genus analytic terms. We spotted some nice patterns, but I'm gonna skip this now. Please comment and ask me later. And let me just take one more minute to summarize. So I hope I convinced you in the first part that the partial wave expansion is the right method to compute S-channel leading logs, computed simply by taking products of the 3-level partial wave coefficients. In a second step, we apply this to the type 2b closed string amplitude. We predicted an intricate pattern of logarithmic structures, and we made some nice observations on uniform transcendentality of subleading logs. And something I didn't have time to talk about is that exactly the same method can be applied also to open strings. For this, you need to have a look at the paper. As future directions, well, hopefully our results will be soon reproduced by efforts maybe from people in this room. As I understand, the genus 2 results might be within reach. And as a next target, from our point of view, from the partial wave expansion, it would be nice to extend our method to 3 particle cuts, which would allow us to access subleading logs. So very quickly, for example, at 2 loops, if we want to compute the single discontinuity, we would need to compute a cut diagram like this. On the left-hand side, a 3. On the right-hand side, a 1-loop diagram glued together with a 2-particle phase space integral. This we know how to do. However, for the single log, there is a 3-particle cut. And unfortunately, this integration is much harder, so it would be nice to think about a method to also trivialize the 3-particle cut. So if any of you has experience with this, I'd be happy to hear about it. Thank you.
Yeah, thank you very much, Hynek. There's time for questions.
Thank you for the nice talk, Hynek. Can you say something about the transcendentality, since you mentioned that?
Yeah.
And I like it.
Sure. Let's go back to the magic table. So as you know, let's go to genus 0. There is a supergravity has transcendentality 0. There is a zeta 3 sitting here, zeta 5. And if you just look at the pattern of the known analytic terms at higher genus, you can kind of make out these kind of trajectories. So for example, the genus 1 correction to this zeta 3 term happens to have weight 0. And if you follow this, to the 6r to the 4 term at genus 2, this also happens to have weight 0. So somehow it's suggestive to make this connection. Something similar happens with the weight 3 trajectory. This term and this term is known. They both have weight 0. And since there is genus 2 correction to the 12r to the 4th term, which sits within this trajectory, we make the conjecture that this term indeed is proportional to zeta 3. And there is evidence from an unprotected genus 1 term, which falls also in this pattern because it is part of the weight 5 trajectory coming from d4r to the 4 at genus 0. And so the way we notice this is that if you look at the subleading terms up here, there is again some combinatorics that at certain orders there are two different ways of reaching that term. And this involves precisely this unknown term, and to make also the subleading logs to have uniform transcendental weights, we landed at this conjecture of zeta 3.
Maybe I have a follow-up question on this, namely the two-loop leading and subleading alpha prime corrections. I think they have a violation of uniform transcendentality. I think the term here has the same transcendentality as the term there, even though they are one alpha prime order apart. Okay, I guess this doesn't have any implications on the two-loop predictions, but I'm wondering whether the violation of uniform transcendentality here, whether it has implications, where is it, 3 loops, maybe it's this field and the adjacent one, that perhaps they're also landing on the same transcendental weight.
I think past this point here at genus 3, I think there will be only leading logs. So this will kind of mask the blue terms here. So I'm not sure we will be.
Yeah, absolutely.
To what you're suggesting. Right, you're talking about this term here.
Oh yeah, sorry, I realized my question is entirely localized on the sub leading logs. Yeah, good point.
Yeah.
Yeah. Yeah.
Sorry, just a curiosity. I suppose that you are working the critical dimension of string theory. Is it right? Yeah.
Yes. This is
if you compactify the theory, for example, the simplest compactification, toroidal compactification, these log structures change or remain the same?
This formalism is independent of the dimension. So as long as you have an EFT where you have massless exchange, this logarithmic structure of the massless logs, this is just predicted by 3 levels. So I think this should go through.
Thank you.
Let me just see whether I understand your final comment on the triple cut and contributing to subleading log. Does that mean that the prediction you are getting in the previous table for the blue entries are incomplete, right? You have to
no, sorry. Yeah, thanks for the question. Maybe I didn't explain properly. We can only get these blue entries because there is no red entry on top of it. So if there's take this term, for example. This is at genus 2, we can predict the leading log, which is log squared. But underneath this term, there will be a subleading log, a single log, and those are the terms I'm talking about. The reason why, for example, at this order we have a blue prediction for the single log is because it's not masked by a leading log already. So my comment is that for example, at genus 2, if we understood the 3-particle cut, we would hope to also say something about the subleading log, which hides below this red terms.
Okay, any further question at this point? Then let's thank Hynek again.